Prova, prova. Prova. Vabbè. Ok.
Oh, questo?
Grazie. Uh, Hi everyone. Today we have the pleasure to have Ameya, who will talk about representational learning and its connections with reinforcement learning. As always, we are Young Verona, and you can find all our events on Eventbrite and on our website, verona.yaml.it. Also, you can find all our other socials like Instagram, Facebook, Telegram, which is the main channel for communication, and also the YouTube link where you can find the recording of the past events. I think that's it. I can leave the stage to Ahmed.
Thank you, Lorenzo. Can you check, Lorenzo, if the sound is okay? Right, it's perfect now. Hello, how are you? I think it's good, yeah. Okay. Just close this.
Yeah.
Okay. No, I don't think you can. Okay, perfect. Okay, good evening, everyone. I'm Ameya Pore, and I am from here, from University of Verona, and maybe. No, it's okay. I don't need. Okay. And I recently finished my PhD here at Informatics Department with Professor Paolo Fiorini. And I also received a joint PhD with Polytechnic University of Catalonia. So it was part of a European Union's project, Medi-Skolotska Reactions project on surgical robotics. So that's my specialization. Right now, I work at the hospital here at the surgery department on endoscopic data, trying to understand, detect polyps, trying to understand the actions during surgery. So more or less, I would say my interest lies on robotics, reinforcement learning, and computer vision in general. That's what I'm going to talk about today. So I'm going to try to connect representation learning with reinforcement learning. So I'd like to thank Cesare Lorenzo for inviting me and also for organizing this RL Odyssey after LLM went success. So I hope you continue this in also other fields of deep learning and AI. So I have put on my slides for today at the QR code here, which I will also share at the end of my lecture. And yeah, feel free to scan it and have a look at the slides. So what we know from last classes, yes, no, So I'm just going to continue from where we left last time, what Lorenzo has been talking about, mostly on different ways of improving RL, Bellman equations, value iteration. So for example, let's start with something very basic. We have something called the Markov decision process. So we have an agent which we put in the environment. And as a consequence, so the environment gives us a state ST, and the agent does an action AT in that environment. And as a consequence of that action, it receives and reward RT. And this cycle more or less continues. So then the agent goes to state ST plus 1, makes another action AT plus 1. And so the Markovian property here is that the agent only gets to see not the history, but only at the current time step. So it only knows the environment state at the current time step and not in the history. That is what is more or less called the Markovian property. So the entire goal of this learning, or what we want to do, is to maximize the cumulative reward. So this reward that we get after each step, we want to maximize the overall reward that we get during the entire episode. So at any point, feel free to stop me and ask questions. I want to make it more interactive as much as possible. And the way it is different from supervised learning, actually, before that, I'll explain this experiment, which from the early 1900s, they put a mouse in the cage, and there was a liver with some food attached to it. So the mouse had to discover that if you press the liver, then you get more food for that. So it's more like reinforcement. So it tries out, does random actions, and once in a while, maybe it pushes the liver. It understands that there is some food, and this reinforces that action, and sort of it does that more times. And there are also like other, the experimenter gave some punishments like electric shocks to punish or to discourage some actions. So compared to supervised learning, what are the additional challenges? One is called credit assignment, which is that if you do an action now, you don't know what will be its consequence in the future. So if I want to go to Verona Portanova, I walk, maybe I go outside, I take the left. So I don't know if taking left here would affect going to Portanova. So the long-term effect, it's very hard to know what will be the effect or the influence of that action on future rewards. Then exploration is a big problem. We want to explore as much as state space as possible. We want to go to new places, want to explore more, but it's very hard to try to make the agent explore. So the problem is that you sort of explore one direction, and then you feel that this direction is giving me good rewards, and you try to keep on going in that direction. So you never try to go in other direction. So exploration is a big problem, and then you'll understand. I think we also did deep reinforcement. So having stable learning is a very big problem. So for example, you understand one direction is good for you, and let's assume you change your direction, you went in some other direction, and that gave you good rewards. So how do we learn from these two things and to make it more stable? It's still a very big problem in RL. And the reason I think RL, in my opinion, it became famous is because of this story from 2015, 2013, actually. This paper was at NeuroWaves, and then it got published in Nature, where they showed that we have this image input of video games, Atari video games from the 1980s, and you can use convolution neural networks. So convolution neural networks had been there since like early 2000s, but in this particular work, they showed that you can use these raw pixel data, pass it through multiple layers, hierarchies of convolution network, and then connect it directly to actions. So it's more or less like an end-to-end learning where you give the raw image inputs to the agent, pass it through some neural network, and at the end you can output Q values, which we saw in last class. Q values or you can also output probabilities of the action uh, as the output of the neural network. So I think what really helped is this, that we had this computational boost. We have increase in power of GPUs coming up at the same time, and which really helped in scaling up the operations. So we could sort of do multiple calculations, iterate over multiple calculations, and that really helped to, at each time step, we are passing it through all this neural network and getting an output. And yeah, that is probably the starting point of this explosion in RL. And then we saw new algorithms coming up. So DQN, which I showed already, it's a value-based algorithm, and it shows they showed that it can learn better than humans on almost all of these Atari games. And there were these new algorithms which they are called actor critique or A3C, which are more like policy-based policy gradient approaches, which are now recently, and all these papers after this, more or less after the recent approaches are based on policy gradients. And so just to give you a glimpse of what is policy gradient, as we saw before in this first slide, we want to, let's call it at J. We want to maximize this function. And to maximize, we just take the gradient of that function. And there's some maths involved here, but the gradient of J comes out to be this. So what this equation more or less says is that we are trying to increase. So the gradient of J depends on the log likelihood of that action times the reward. So for example, if the reward is positive, then your update would be in the direction of increasing the likelihood of that action. So we try to encourage that action because it's giving us more reward. While if the reward is negative, then our gradient would be in the opposite direction of the log likelihood of that action. So we are punishing that action. So for example, if we have these three trajectories, one of them is giving us good reward, one of them is giving us bad reward. So the bad reward, so the sort of the function, the value function or the policy function would more or less look like this, where uh, the trajectory with very less rewards gets discouraged, whereas the trajectories which fetches more reward, you increase the likelihood of those actions, and that is basically what is policy gradient. So all these algorithms which are used now, like PPO, which is one of the most famous ones, are based on this theorem. I think the new things that are coming up now is how do you reduce the variance in the update, but more or less I think the equation remains the same. Another milestone, I think, in this story is AlphaGo, and the reason it learns, or I would say the reason it became like a big story is because Go is a game which has lots of possibilities. It's more complex than chess. It is at each time step you have multiple actions. It's way more than chess, and that's the reason that this became famous. Also, it defeated like 18 times world champion that time, and then Alpha Zero came in 2017, where they showed that you can learn directly from self-play. So the agent played with itself with another agent and learned from interactions with each other. So in AlphaGo, they used human data, and it's more like imitation learning. So you used data from humans who are playing, and then use that to pre-train the model. And then Alpha Zero was basically learning everything from scratch. And then comes the robotics, some of the success in robotics. Uh, this is an algorithm called TRPO or also PPO, where you see that The agent is trying to walk, learning to walk, and more or less this is how it learns. So this algorithm in particular, as I mentioned, that it uses the policy gradient, but it tries. There are some tricks that they do to reduce the variance in this reward. So more or less, adding some advantage, adding some baseline in this term here, and it seems to work. But it's still not a well explained problem, well explained algorithm. It seems to work, and we don't know why it works. So now in here at Verona, we use similar algorithms, and this is some of our results. We trained some robotic surgeries. So this robot is called the Da Vinci robot, which we also have here at the Altair lab. And you can see the learning behavior. So at first, more or less, at the beginning, you can see the robot has no idea what it is trying to establish. And slowly it learns this behavior of picking up the fat tissue. So we want to do that in order to expose the tumor or the cancer tissue which is underlying there. And then once you learn the policy, you can directly translate that in the real robot. So we have the real robot as well. And we showed that you can train in the simulator. It's a simulator we developed in Unity. And once you train that, you can test the policy, train the policy in the simulator, and then test in the real world. And also, some of our experiments in colonoscopy is you take this image directly, and the reward function here is trying to minimize the distance with the dark pixel. So we want to navigate the colon and go inside to reach the end of the colon. And the reward function here is reduce the image center and the distance between the depth of the image, which we detect by dark pixels. So we train in the simulator again, and then you can see that you can test in the real robot. So this is a colonoscopy robot that we have, where we use an external magnet to control a capsule at the tip here. And we see more or less it navigates the entire colon using RL. So the reason that we use RL is sometimes there are situations where you can't detect this depth or the dark pixels. And in such situations, you need some kind of adaptability, which reinforcement learning gives. So what are we going to discuss in this talk? We're going to discuss about representation learning. What is representation learning? What we call good representations, and how do we learn them? So what I showed before, it's more or less comes in this paradigm of end-to-end reinforcement learning, which is that you have these pixels, raw pixels, and you pass it directly through a network, convolution network in most cases, and you predict out actions, a probability of actions, or you can also predict out the Q values. So what this does, it learns this mapping from a high dimensional space, which is pixel level input, and it outputs directly the actions that we want to do. So neural networks are more or less, they are like universal function approximators. They can approximate highly nonlinear functions, and that's the reason it seems to work. But what are the problems now? So this definitely can't be applied directly in the real world. It can be applied in situations where we have a lot of data, like video games. We can train on tremendous amount of data, and we can have the agent learning for hours. But it's not possible in robotics or real scenarios where collecting data itself is a big problem. So data inefficiency is I would say one of the biggest problems for reinforcement learning algorithms currently existing, because they require millions of transitions, very highly sample inefficient. So this work, for example, compared human performance with DQN, and as we expected, it turns out that humans require much less amount of training data, amount of game time to reach good score, while you can see like DQN or all other variants of it can surpass human score, but it is very inefficient. So this is like orders of magnitude inefficient compared to humans. And so learning from, as I said, learning from high level space is very complex because, for example, each pixel in your data in the Atari game can take a value from 0 to 255. So it has it's a very, and it can have noise, a lot of noise. So it really doesn't give us the real picture of what the real environment state is. So that's why there are comparison between image-based inputs and there's comparison between state-based inputs. So state-based inputs are vectors or numerical values, which more or less give us the real ground truth environment state, while image-based inputs are noisy images or direct pixel values. So what we can see in this plot is that when we use uh, state-based values, numerical values, learning from them is very efficient. So for example, if we directly take the joint angles of the robot, like in this case, the locomotion or pendulum swing up. So if we directly get the joint angles, use the numerical values and put it inside the network, it is very easy to learn from those values because they are real ground truth values. But if you take image, put a camera and then use the image as the input, then it's very inefficient. And that's what we see in these curves. Like this is the blue curve here is the learning from state inputs, while the green curve is learning from images. So learning from images is very inefficient. And the question is, how do we close this gap? One of the solutions could be good representations of this noisy input of this image, or compressed representations can accelerate learning from images. So generalization, what we are good at, what RL algorithms are good at right now is doing one single task and reaching high rewards. So we are, as I said, like Atari games, it is very good at one particular Atari games. Playing chess, it's very good at playing chess. But if I ask it to do something else, it doesn't have any idea. So very less generalization works very well in a single task setting, but when it comes to other different tasks, multitask, it really fails. So to give you an example, if I ask you to play any video game, let's say Super Mario, you can complete, let's say, level 1, and you more or less get an idea of how to play level 2. It's more or less the same agent and the same control, except what changes is the background. So if I train you on this, you wouldn't take a lot of time to adapt to level 2. And that is what most of the algorithms fail, is that for them, it's completely new pixels, new state, which they have never seen before in the training. And yeah, so the performance is very low. So if I just train it on level 1 and try to test it on level 2 of Mario, it fails terribly. And so this plot, for example, is what it shows is the amount of training and for testing. So test is on unseen backgrounds, for example, and training is you train it, for example, on level 1 and you test it on level 2. So for example, there is a very big gap here. And as you increase the training levels, you try to close the gap. So the agent becomes more versatile, can learn more from training. And this gap sort of closes down. Now, it requires a lot of supervision. So generally, RL, you need a very dense reward function. So every step that you take, you need a reward for that. And generally, that's not the case with real world exploration. For example, I have to go to the train station. I don't get a reward for intermediate steps, or I get a reward at the end. So it's very sparse reward setting. And so using such sparse reward, how do we learn from such sparse rewards is still an open problem. And one of the solutions that I will discuss is that instead of only learning from reward signals, which are very sparse, we can also learn from unsupervised learning. So we have this visual stream of data. We are seeing from here, I'm going to Verona, I'm seeing everything. How can I use that to learn maybe how the world functions, the world models, or the world models, which I'll come. And also exploration, which I mentioned, is still a challenging task for RL. And if we have good representations of the images or what we see, we can help in exploring effectively. So this is what I mentioned by sparse reward. This video game in particular, it's called Montezuma's Revenge. And it's very famous because it's one of the toughest game to solve, because the agent has to do all these big sequence of actions, like go down, take the key, come up and do this big sequence of action to get one small positive reward. So unless it does this sequence correctly, it doesn't get any reward. So it's just trying to explore randomly. It takes a lot of time step to learn any effective goal-directed behavior. So that's why end-to-end learning, which I mentioned before, is generally not preferred in such cases where the reward is very sparse.
So if you apply negative rewards, like have dense rewards.
Yeah, you can do that, but you have to put your more knowledge more in, you need to be expert in that video game to know how it functions, right? So it's more like you can do it, you can design dense reward functions, but it's very time consuming. It's very, we don't want to do that. We want to learn maybe sparse reward settings. It's possible, like that's one of the things people do. If for example, picking an object is very hard, so just design a reward which is very easy, like minimize the distance with the object and something similar.
Good representation, I didn't get what you mean.
Yeah, I'll come to that. Right now I'm just telling you what are the problems with end-to-end learning, and then I'll come to what are good representations and what do I mean by representation. So this is like generally how sparse reward looks like. You train, you explore a lot, go to random directions, do everything, and you don't get anything. No feedback. So there is no learning here. So we are just seeing everything randomly, but we are not using it to learn. And you get a reward after a lot of training time when you do a lot of sequence of actions. So very, very inefficient again. And also there's this problem of adversarial attacks. So we want our algorithms to be robust enough. So for example, image classifier, like big ResNet, which are already established, like image classifier, they are trained on object detection, like thousands of objects, millions of objects. So for example, one of the example I'll give you here is that this network thinks this is panda with a confidence of 57.57%. And if I add a bit of noise, just a bit of noise, for any human being, this thing looks the same. It's more or less indistinguishable for our eyes. So this is panda, is the same as the first image, but it's with the noise, very few noise, because I'm controlling the noise with this value epsilon. But for the network, for the classifier, it seems as a gibbon with 99% accuracy. So there are these things which are called adversarial network, introducing a bit of new things that it has never seen in the test training data can lead to like tremendous failures, misclassifications. Also, we want transferability. So if I know how to play this game, which is, I think this game is called Breakout, which is we want to move the paddle to control. We want to move the paddle to control the ball, so the ball hits everyone. So let's assume we know how to play that game. Now we want to use that skills to play other aspects of the game. So if I give you another game with a bit of different block setting, translated, for example, in this case, translated paddle, random target juggling, for example, this for us it's very easy to adapt because we know the skills that are involved here, and it's more or less the same that are involved here. But for the RL, you can see here, if I train it on standard breakout, which is here, and for example, this is offset paddle, so it reduces from 36%, 36 to 0.6. So it really fails tremendously miserably in all these different versions. So there is also no transferability in end-to-end. And what we desired really is we want our system to be general, which I showed you before. We want it to be robust. We want to use the skills that we learn during learning into other tasks, and reusable like this, for example, also flexible, I'll not go in the details of compositional, also interpretable. So we want to know why we are taking the decisions that the agent is taking. So to summarize, we find ourselves in this situation where we more or less know now, or we have worked out the formula to how to solve one single task using end-to-end. If we have enough data and if we have enough compute power, we can solve each of these separately, and we can become better than humans at each of these. But the next generation of AI probably in RL is this thing where we want to make robust, we want to make efficient systems which can solve different tasks, maybe using the same representations. So what kind of representations we want to learn? Well, does the representations here need to be hierarchical, flat? All these questions so these are the questions I think the community is trying to answer these days. So what is representation? So just to quote some of the big names which have worked in RL, more or less deep learning. So Yoshua Bengio, he says that learning representations of the data makes it easier to extract useful information when building classifiers and also other predictors. Another Benjua quote here is that if you can build models of the world, if you know how the world functions, where we have the right abstractions, where we can pin down those changes to just one or few variables. So if we know what variables are changing in the world, then we will be able to easily adapt to those changes because we don't need as much as data and as much as observation in order to figure out what has changed. Then there is Jan LeCun, who says that the idea of learning to represent the world before learning the task is what babies do, and something we can also be inspired from. And I don't know this who has this quote, but really I think it's a way of injecting the knowledge that we have in the learning aspect. So we don't want to learn everything from scratch. We don't want to learn everything, all the behaviors from scratch, but we have the knowledge of the world, how it functions. We want to put that in the learning. And how do we do it is the question. So what are representations? Just some definitions which I found in neuroscience and cognitive science is that formal systems for making explicit certain entities or type of information together with specification of how the system works. So let's try to unpack it. So if I give you these are like three different ways of writing 37, and we say these are three different representations of 37. And while the information in all these three cases is the same, but their representational form is different. So what this implies is that the information content is orthogonal to the representation. So how we represent that thing is independent from the information that it has. And so representational form is orthogonal to the informational form. Generally, we use the abstractions to make different computations more efficient. For example, in Arabic, 37 is more like in the power of 10, whereas in binary it's in the power of 2. So it depends on what type of computation we want to do. And finally, in order to truly understand this representational form, we have to think of the space in which it lies, in which the representation lies, and not a particular point. So rather than thinking of any individual point or data in isolation, we want to think of the space, how it looks like, manifolds. So what are good representations now? I'll come to this aspect, which is called invariant representations, where, for example, we want to learn to drive in this car. We want to learn to drive this car on this road. Now, all these other representations, for example, the cloud, the house, are irrelevant for the task of driving the car. So what we are saying is that these two images in the representation space, we can also call it the latent space, they converge to the same point. They are more or less, they are mapped to the same point. Whereas this image here, which is task irrelevant, you map it to another point in the latent space. So it doesn't, so these transformations, for example, the change in color of the car, or yeah, that's the only thing different, or the shape of the car is irrelevant. And we want to remove this, for example, the background, which is not very relevant to the task. So any questions here? I think this is one of the probably important aspects.
Attention to the transfer. You have to pay attention. The classification. Things like that. We don't care about the background, we just understand the patient. For recognizing that, we just need to pay more attention to the patient.
Some aspects of the image, yeah. And that is what is like, maybe this is what it means here, is that if you apply this transformation G to your input, and then you apply F, so more or less both of them point to the same point in the latent space. So the representation remains unchanged when a certain type of transformation is applied to the input. That means, like in this case, if I change the color of the car, the representation remains the same. But if I maybe like change the background, it changes. Also, there is this fundamental idea in physics, which is finding symmetries. So symmetry is a broader concept. It's more than like butterfly wings, which are symmetric. So symmetry, it sort of represents the cores which remain unaltered, which don't change under transformations that could change them. So let's pack this using an example here. For example, there is a spring mass system. I translate the system, and then I put it in time, so forward the time. And then in the other case, I do the opposite. So I forward the time first, and then translate the system. So both these transformations, we reach to the same point, same system. So we can say that this transformation is symmetric to this transformation. And similarly, when we have 3D objects, translation and scaling of the object. So when we first translate and then scale the object, we reach the same state when we scale first and then apply translate. So these two transformations are symmetric to each other. And that's what where we come to this thing called equivariant representation, where the goal here is to preserve the effects of transformation G in the representation space, so that the input is translated, and the representation. So what it means is that if you apply some transformation in the image space, the transformation also is applied in the representation space. And that's it. So if I apply like first, if I apply G and then if I apply F, it's the same as applying F and then applying G. And this is where we come to something very important called as disentangled representation learning. So let's assume we have these ground truth factors of variations. So these are like different aspects which are changing. But what we want the agent or the system to understand is, if I just show you these images, can you give me the latent representations of the factors of variation? I think this is one of the most important points, which also it's a very hot topic everyone's working on right now, which is how to ensure we get disentangled representation. So this image here, it's an entangled image. It's an output of everything that comes. And we just show this image to the agent. And using this or using these different images as the input, we want the agent to understand that these are the features or these are the latent variables that are different in these inputs. So generally, when we have like end-to-end learning, we don't understand what are the features. It's just some random features which are not like humanly possible to understand. But we want to have this change from entangled version to a disentangled setting. So what it means is that if I change just the orientation of the robot or just maybe shape of the object, that should not affect everything else in the image. Yes.
Looks like we are sort of
Yes, exactly. That's where I'm coming now. And that is how encoders and decoders became like probably very famous. Exactly. No. So I think that's one of the motivations of encoder and decoder structures, that we want to have these different we want to control the latent space. So if you just have the encoder decoder structure, it's still hard, but then you can put some more constraints to establish this disentanglement. And so representation learning for RL now, where do we come? So the point here is that first we learn to see, first we learn to summarize the input into a low dimensional space, into a compact compressed version, and then use that for the policy, for learning how to make decisions for the RL part. And then we hope that really this information is enough for the reinforcement learning. We don't need to deal with very high dimensional space, but this compact version has some of these, let's say, invariancy or equivariancy or disentanglement, something inside this, which will help the agent to perform or make good decisions. So just for putting it formally, for every input in H, there exists a F or a point in this space, capital F, such that the Q value function, such that you can use this F for the Q value function here. So this is how it generally representation learning algorithm works. You have a representation space, capital F, and you start it with it's an empty space, and then for every iteration, you try to learn this space, learn some structure of the space, and then once you have something in this space, then you learn some policy over that. So execute pi, which is the policy, and then add the experience that you get inside this replay buffer, and then you sample out from that replay buffer, learn from that, update the representation space, and this continues. Now, what seems to work really is And this is very strange for me that these papers are very recent. Let's say 3-4 years ago, and all that the new things that they do is add some data augmentation. So the idea is now we want to learn a good space. So what do they do is just add some augmentations to this space, and these augmentations are basically very simple augmentations: crop, translate, window, flip, rotate, and random change the colors. So you have this in one image, which is your input. You add augmentations to it. You add change the input, uh, which is just change, rotate it, translate it, or do some very basic augmentations. And it seems to work. So surprisingly, data augmentation, it really has been adopted recently. There have been like 3-4 papers now, ICLR 2021, and this is how the generally the pipeline is. You have a replay buffer, you add augmentations to the image, and then you pass it through actor and critic. So I think the idea here is that we want to increase the variety in the data. So the algorithm more or less sees different variations in the learning, and that's how it works. So there are still some issues that we are unclear what are augmentations which are good for RL, which are good for reinforcement learning. In particular, for example, state-based control, we don't know. It generally for image-based inputs, it's easy to find these augmentations. But for when you have like numerical values, state values, is hard to add augmentations to them. Add noise maybe. I'm not sure. And so one of the workaround has been that you just use standard augmentations which have been existing there for in the computer vision literature. Question?
If we have a good representation of the data space, so we can like generalize of some problem seems to be solved. But how we are training, and what's the last function for the training the latent space? I mean,
In this case, it's just the same loss function as reinforcement learning loss.
we don't have the policy. So latent space to the policy, we know how we can how we can.
Yeah. So actually, in this particular case, the loss is the RL loss, okay? And we are not concerned with what is the input. So we are just learning on the RL loss. But I'll come to approaches where we specifically learn this part first, learn how to see, and then learn how to act. But like what is surprising for me is this fact that you just add these new changes, just input, add some augmentations to the change to the input, and performs very good. So not all standard augmentations that are existing in computer vision literature, they can be used in RL. For example, this particular augmentation, which is random shifting. So you just shift the position of the agent to different parts of the image. Seems to work very well. But there are also all these different types of augmentation. How do they work? And some recent works, this paper, particular 2021, they try to understand which augmentations are better for that task. So automatically selecting the augmentations. Also, this data augmentation prevents overfitting. So for example, in this case, is the same encoder or the same representation learning part here. What is changing is just we are adding augmentation here, and we are not adding any augmentations. So this thing really helps, and it improves, like basically you can use any encoder and it learns to perform. So when you overfit the neural network, for example, when you are overfitting here, every time the episode resets, you have new initial conditions and the agent forgets. So that's why the learning curve is not very high. Whereas in this case, it is learning based on different varieties of augmentation. So it is learning pretty good. And then also, if you see here, this is state-based input, which I mentioned before. How do we close the gap between state-based learning and image-based learning? So just using augmentations, I think we are still coming closer to this line here, which is learning from states, numerical values. And also the time taken for learning is very fast, which is also very surprising for me. So this was about augmentations. And so I'll just maybe we'll take a quick break for some time, and then I'll come to decoder, encoder. So where were we? We were trying to learn some representation first, and then the policy first. So starting back again from here. Now there are three ways of explicitly learning representation. So what we want to do now is to control the latent space. What are we learning? And there are like three main ways. One is through encoder decoder. It's called generative modeling, where we are trying to learn the data distribution through generative modeling, generally through reconstruction loss, something like that. Then we have contrastive loss, where we try to say that we use a classification loss, like in general classification, to learn some representations, and then we try to preserve the temporal and spatial data consistency. And then we have the self-supervision, where we exploit the knowledge of the data. So we are using the data itself to learn some patterns in the data. And I'll come to each of them now. Let's look at generative modeling first. So we have this, maybe I'll just go very quickly into the story. So we started with normal encoders, where you have this image input, pass it through some encoder queue, and there were individual values in the latent space. So that is what is called encoder. And then you use those values to reconstruct back the original image. We call it P here. And so essentially what we're trying to do is force the network to go to a low dimensional representation, and then construct it back. So we are trying to learn only the information which is relevant to reconstruct back the image, or the most important part that really matters in the image. Now this, when I said normal autoencoders, there were these single values here, discrete latent spaces, and it really did not turn out well. So there were some problems. It did not scale up well. And so someone came with this idea that let's have some distribution here. So instead of having these individual values, each of this is now a distribution. So it can be any different distribution. In this case, it turns out that the normal Bayesian distribution works very well. And so you see here, the latent space now is, you have a mean and you have a standard deviation. And then you use this distribution now to sample from this distribution to reconstruct back the original image. And this is what is called VAE, variational autoencoders. So we have, in the loss function, we have the reconstruction loss. It comes from here, which is pretty straightforward, which is maximizing the log likelihood of this. We want to match this with this X with Z. But what is interesting now is this term, which is called the KL divergence between two different distributions. So we want our distribution in the latent space. We want to force it to be a normal distribution. And that is what comes from here. So more or less, this sort of gives us control of what is happening in the latent space. And we want to have this normal distribution, because then each of those would be independent of on one another. So the idea is that each of this latent variable in here will be independent of each other, will be orthogonal to each other. And that's what we want to do. So it's more or less, if you see this latent space, it's a matrix which is diagonal, unit one, and with normal distribution. And so this gives rise to the disentangled behavior, which we talked about. Each of the variables that we have are orthogonal or independent from each other. And now this paper, what they do is saying that we can add more weight to this scale term and try to reduce the reconstruction loss term weight. So this beta sort of gives us control of, we want to control the latent space more than our objective of reconstructing. And turns out that if you put a value of beta of, let's say, more than 1, then it learns a disentangled space. Also, it sort of makes it more orthogonal. It makes it yeah, more. That's the only reason you have this beta. And so here we come. Having this, we have a disentangled structure of the latent space. And this paper particularly showed that you can now change one of the variables to change, like, for example, in this case, you change one variable, which is representing the skin color, and you get these different, different complexions for people. Also, you can have this another variable, which is age. So you can consider latent space Z, which is composed of, let's say, Z1, Z2, Z3. And you change one of these Z's, you can tune these, and this is the output that we get from that VAE. So we can change the age, we can change the saturation of the image, brightness of the image, which is very cool. So we are getting towards interpretable variables, which we can change, and it results in a output that more or less what we want. We understand. And that's what they did for RL. So for example, you have these two images. In one, you have, let's say, yellow and blue boxes. And in the other one, you have different backgrounds and also like different objects. So when you do end-to-end learning, let's say the agent knows these with the yellow with green background, and then you have, the purple with green background. During the target, when it comes across yellow with red background, it doesn't know how to act, because it has never seen it before. And that's why this setting it fails. It doesn't know how to act. But when we use a encoder here, which we train on, these are our source domain. It knows, it sort of has this disentangled structure of what is background, what are the objects. And so when we give this target domain, which is with different background, but with the same objects that we use during training, it go. Oh, I don't know bad. What is bad? I mean, it performs very well. So that's what is the output of this paper, that you can use different objects with a different background that it has not seen before, and it has learned this disentangled setting, so it can perform well. Also, in the robotics domain, if you see, you can just change the color of the cube, and changing the color in the simulator, it performs well, and also in sim to real, which is translating from the simulator to the real world. Any questions? I think this is what we are talking about. So using the disentangle structure for RL. So if you have a good disentanglement, you can change different objects, maybe different backgrounds, and you can still be able to adapt to your training setting. And which is which is a good insight or good direction to move into multitasking or probably testing on unseen scenarios. And so this is one of our recent works. What we did is, so we added distractions to the RL agent, but we use an additional information of mask. So what I'm saying is that instead of disentangling into whatever you want, I want to disentangle between agent and what is environment. So I give information of what is the agent in this task, in this image, and the rest, it should try to disentangle the agent and the environment. And so that is the idea here, that you have this agent, you pass it through an encoder, and then you have the latent space, which consists of agent and environment. And the new thing that sort of we have here is that we try to maximize the distance, make these two representations orthogonal to each other. So making the agent representations independent of environment representations. And how do we do it? So we use the masks here. So there is this ZA tries to reconstruct back the mask of the agent, which we already know. Let's assume that we have access to the mask. So we learn ZA using the mask, and then ZE comes from just orthogonalizing these, making a vector which is orthogonal to this vector. So what we are saying is that this is implicitly the environment representations, and that is the agent representation. And it turns out that using such an approach, you see the curve, it learns very fast, adding this particular loss function compared to other work which also used masks. When you have this disentangled structure, you can change the backgrounds, put any backgrounds, and you can still learn very fast on these different environments, here. Now you can also add noise. So instead of a perfect mask, oh no. Instead of a perfect mask, you can add a noisy mask. You can add a very approximate mask, which is not the real perfect shaped mask. And you can use these additional information to bias the network to give more information of what is agent and what is environment. And this really improves the learning. So I think that's one of the point here, that if we can put our information, the knowledge that we have, using anything, that would help improve the learning somehow.
Is the mask just another information, or is masking out the rest? It's just in addition.
It's additional information. Yeah. So we just try to reconstruct the mask here using this ZA. So what we are saying is you are learning features of the agent in ZA, because you are only reconstructing the mask and not the environment. And what features are here are just orthogonal to this. So they are independent of what is mask. So whatever is not mask is the environment. And that seems to work. Yes.
Implementation, or like noise doing training, or did you try it directly on the test? Like you showed that it's robust to noise. Like, did you train with noise, or did you directly test it?
No, in this case, we trained with noise, but I think it would be interesting to see the generalization to testing on with like noisy mask while training on perfect masks. And so this comes closer now to idea of intuitive physics, which I find very interesting, which is that we humans, we don't need to know these laws of motion to predict the motion of the objects. We understand them just by looking at them. Uh, so there is this work which what they did is more or less, I will not go in the details. It's not about reinforcement learning, but if you see this scenario, there are two blocks here, and a ball comes from behind and it passes by from left to right. So this is a physically possible event. So when you see the block comes here behind, disappears behind this block, comes and again disappears and comes out from here. So similarly, these are physically possible events. And then they came up with physically impossible events in this case, which is that the ball comes from the left and then it doesn't appear in the middle and then directly comes out from the right. So these are physically impossible events which they generate in the simulator. And the idea is that when we are kids, when we are small kids, when we sort of do well to kids, they get surprised and they measure this surprise of the network. So it's called violation of expectation, which is if you see a physically impossible event, then the agent should be surprised to see that. And then more or less you learn this aspect of intuitive physics, that how things work in the environment, how things move more or less. So coming to the next part, which is contrastive loss. The idea now of contrastive loss is that we have an anchor X here, and then we have a positive sample and a negative sample. Now, what we want to do is to reduce the distance between the anchor and the positive, and then maximize the distance between anchor and negative. So that is the objective of contrastive learning. And so the idea is that learn features that are common between data classes and features that set apart data classes. So we want to learn features which are common in these data positive and anchor, and then we want to set apart the data classes from other where the features are very different. So I'll explain it what it means. Anchor is the input. Let's say this, for example, this is your input. You say this is anchor, which is a cropped version of this. Now this you add another maybe augmentation to this, and you have you sample out another image, which is another state. So what you're saying is that these two are closer in the latent space, although they are spatially augmented, but these two are very far away. And so this is called the contrastive loss. So these two come in the same class, while these two appear on two different classes. And so I think what we are learning now here is this temporal aspect, which is these are temporally similar in time, and these are temporally different in time. And so this paper was actually very, very big. It's called CURL, Contrastive Representations for Reinforcement Learning. And so this is the idea. You have this replay buffer where you put all your experience in this, and you take an observation, add data augmentation, and have that contrastive loss, which comes here. So you have another aspect which comes from here, where you decrease the distance between temporally similar and increase the distance between temporally far away agents, temporally far away scenes. So during what happens, this is the reinforcement learning loss, which is the normal loss that we have, policy loss. And then during for contrastive loss, what we do is you just so make a copy of this encoder, freeze the weights, and extract the features here. and then use the contrastive loss, which is this loss which comes from here, which is features of these two come closer, features of these two far apart, and compute that loss and then backpropagate only in this encoder. So that's how it works.
You want to find the negative anchor based on the temporal time. So it can be like a trouble because imagine after 10 after step I came to the similar this state, but I'm so far. But the next step is so different. So I just say this one is the positive anchor, but it's not positive anchor. This is the negative anchor. I mean, if we want to define the positive and negative anchor based on the time step, so it can be getting a trouble because imagine the next time step is completely different situation, even the can have like a bad.
No, but generally it's almost the same. What do you mean completely different? Let's say you're walking from here to there.
So the next step is completely different. I'm falling, I don't know. Again. So, but after 10 steps from this state, I'm similar to this state. If I want to define this step as a positive because it is close to this state, so I say make this close, but it should be more far away.
Yeah, I think the assumption here is that states which are close have not much differences. Not much differences.
State, because imagine video camera 60 frames per second. It means that like 60 steps away from now, just 1 second has passed. And is much more likely to be similar than what happens in a minute. Same, I guess, applies when you play chess. So next move is very similar to previous move, where, I don't know, 100 moves down the game, then the whole chessboard is different. Then, of course, I agree with you, there might be some similarities by accident, maybe not in chess, but in something else.
But there are very few exceptional cases of that.
But in the overall amount of data, then they kind of have low. I mean, there was something similar for, I guess, Clipper, where they were doing contrastive learning with random images taken from the web. So there might have been like a picture of a swan, which was written swan, but it was a dog. And then with another dog, and it actually, you would have said those two are different, but they were actually equal. But in the overall settings, they are just very few. And so the contrastive learning means brings things similar with a similar representation and things far away. So maybe they will get a step in the wrong direction over maybe 100 or 1,000 steps in the right direction. So it shouldn't affect too much.
But we never define the positive angle based on the value of the state. Because it can be also more, can make sense more.
But it depends what you mean for the value of the state. If it's a picture from a camera.
No, actually, I know some work which use the reward that you get as the action as the point of invariancy. So if you're getting more or less the same reward and doing the same action, that means that state is probably same as the other state. But I think it still doesn't work very well.
It also depends on how you're playing the Pore game. Then maybe minute 1 and minute 20 may be the same because the state of the field doesn't change much, but it is chess, then it's definitely different. So it really depends on the settings.
For video games.
They have the agent elements to work probably. It looks similar, but also you can do it by doing augmented versions. So you say this is a dog, and then I make it like less bright or more bright, and you say it's still a dog. Straight, same image, same state, but with variation. But that's my understanding.
Yeah, exactly. Yeah. So what we see now using curl, we are getting closer to state-based learning performs like quite good compared to all other, performed well in 2020 compared to others, and was very close to state-based SAC. What else here? So now comes this new work from ICLR 2023 last year. What they try to do now is add disentanglement on top of contrastive learning. So what this loss does is you have this, for example, in this case, agent at state ST, then you have agent at state ST plus 1. Then you have another episode here from another episode, and then you have an agent from the same episode, but which is temporally very far. So temporally very far, another episode, T plus 1, and then timed step T. So what they're saying is the first two are close in time, so they belong to the same class. The first and this one, which is from another episode, they are non-temporal and different episodes. So this comes here. And then also first and last are non-temporal. So we are also learning disentanglement based on color. So you see there are different colors from different episodes. So this is more or less like spatiotemporal disentanglement. So we are learning what is changing in time, but also what is changing in space.
Say class.
Ah,
Don't have any classes.
classes, literally classes. Like for example, you see here, this belongs to one class. This belongs to another class. So that is what is contrastive loss.
Okay, but still contrastive there.
Yeah, it's
When you say classes, it means bring them closer.
bring them closer, exactly. Yeah, this is also contrastive. You bring the first one and the second one closer, and all the other pairs far away. And so in my opinion, it's coming to that point where we are understanding some of the object properties like color, shape, object permanence, what is moving in time, understanding the physics. So I think we are very recent, like people are coming closer. And also this gives like a good transferability. So you see after this line, they change to an unseen colors, unseen environment. And you see the adaptability here is pretty good when you use this TED. Also for others. So if you see curl, which I showed before, so curl learns the swing up, but then it fails, comes down. Also curl, the adaptability is still good, but TED, in this case, it's called TED, temporal disentanglement, performs. The way they sell this work is improved generalization in reinforcement learning. So it is able to improve the generalization. So yeah, also this work, I think from 20. Hey, come on. Time contrastive networks. So the idea here is that you record multi-view points of the same event happening. So you're recording from two different cameras, pouring water or doing the same thing. And you do the same thing in the simulation. And the idea here is that now you synchronize them. And what we are saying is these two frames, which are from two different angles, are closer than these two frames. So is the same contrastive loss here. And what we are learning is the invariancy for the angle. So you can see the same event from different angles, and you can identify features which are important to that event and which is invariant to the angle from where we are seeing that. And once you learn that, once you have trained this TCN, then you can show it one demonstration and then try to imitate that using the robot. So you extract the features of that task, and then bring those features closer to the features that you extract from here, and it learns to pour robot using a robotic arm. So it's more or less like imitation learning, self-supervised imitation learning. And I think the surprising part is it's a very old work from 2018, 2017. Okay. Also temporal learning through shuffling. So you take a sequence of frames and then shuffle them and then learn to put them back. Also, that's a very interesting idea in my opinion, that I think this work is from CVPR last year, still very new. So the idea is you have this input, you add some spatial augmentations, change colors, rotations, and then you shuffle the frames to each other. And what we try to say is that this spatial augmentation, they are close to each other. So on the top row, so reduce the distance between the top row and this, whereas temporally make these two far. So using contrastive loss, we are trying to learn how to rearrange back to get the same video. So learning the temporal features and then also learning the spatial features here. So when you add data augmentation. So I think it still needs to be applied to RL. Probably someone is working on this, but I think it's a very good direction as well. Now coming to the last part, which is using the data itself to learn maybe what I talked about before, like when we don't get good rewards, then we see things, but we need to learn from them. And so how do we learn from them? Unsupervised learning. That's what will come here. So the idea is we first learn how the world works. So let's say using the current state, which I see, predict the next state and the reward function, which is called forward predicting. And the second thing is inverse dynamics, which is predicting the action that generated the transition from S to S prime. So we have S prime, and we are trying to predict what is the action. And this is what is forward dynamics modeling. We take the state, we take the action, pass it through some encoder, and we try to get what is the next state. So when you do it for a long number of many states, you sort of learn how the world works or how the agent is working. So the problem with this is directly using pixel level predictions. It may be very complicated, and it's always good to go into latent space and then use a more compact version. And that's what maybe 2017 that's what this work did, is you have a encoder, so you pass this image to an encoder, get the encoded features, and then concatenate it with actions and try to predict the latent features of the next state. And I think, in my opinion, that's what there are these more representative works called Dreamer, different versions of Dreamer. And the idea is that you first try to learn the latent space. So in this case, there is this recurrent model, something like LSTM, where you learn Z is the encoded version, and you also use the H, which is the recurrent. So information from the previous time step to generate Z. So the Z loss function here is reconstruction loss, the encoder loss, plus the recurrency loss, which comes from here. And the idea is that first you learn how the world works. It's called the latent space dynamics model of the world. And once you know how it works, then you try to make predictions. If I take one action, where will I end up? And sort of imagine the way we imagine what action should we take to to plan. And I think it works very well. And the idea is also very cool. It's more like model-based learning, where you learn the model of the environment first, how the environment functions, and then you learn how to plan in that model world. So for example, if I know that the bus for Porto Novo comes every 20 minutes, then I will plan my actions according to that model. And yeah, I mean, it's like always they show their performance is pretty good on different benchmark. So what I've noticed now, like these days, you have to have benchmarking not only on one specific Atari or one specific environment, but you need to show it on like various different environments to show that it really works. For 3-4 years ago, I think you could just show in one of the video games and it was okay. But now you have to like show robotic DeepMind labs and all these different things. So forward models have to concentrate on each individual pixels. So to reconstruct back the image, which are pixel level reconstruction. And the problem now is, which needs inverse dynamics. So for controllability, we also need to predict the action and ignore the irrelevant parts of the state. So what does inverse dynamics means? We have the features of the state, features of the next state, and predict the action which resulted from this state embedding to the next state embedding. And so the idea here is that sometimes there are elements in the states which are not under your control. For example, if I give you this video game, which is a lot of noise. So in such a case, just using forward model, which is using your current state and the action to predict the next state, you will always predict an incorrect next state because it's noise. Like this thing is very hard to predict. It's pure noise. And so in such cases, you just need to look at features which are relevant to your task. And that's what the inverse modeling does. So what they do here is that you learn features which are relevant only to your action. So that is the idea here, that in such situations, the agent gets stuck. It will just keep looking at this thing because it's a new state it has never explored. And the forward model tells that it's a new state every time and your prediction is not correct. And so in such cases, you need inverse modeling where you take state st plus 1, take state st, and then predict the action that happened between them. So you are learning features which are important for that action. So all these features like the noise are irrelevant and the agent would start ignoring them because they're not relevant to the actions. And so this is a very good paper called Curiosity Driven Learning Exploration, where if you want to explore, the way to make the agent explore more is by giving it another reward for when it goes to a new state. So for example, if it's in state st, if it has never seen st+1, if it has never seen a new state, and if it goes to that state, then it gets a reward for that. So exploring and going to new places of the environment gives you more positive reward. So it's more like curiosity.
that because that pure noise will keep
Yeah,
generating
exactly. That's why they have the inverse model. So you have the with the inverse model. So when you don't have the inverse model, you see the green, it gets stuck in such situations. Well, whereas when you will have the inverse model, the learning is better. Now coming to this part where we are using pre-trained models. Now we are moving into big language models. We are moving into big models, which are very hard to train in our local GPUs. So the point here is that now the phase one of the learning is you just train the perception model, learn how to see on general data sets like ImageNet, any big data sets that are available. And the second one is now fine tuning that model, that network which you have uh, on your policy, on your task at hand. And that is what still a very new, not very, but 2022. What they do is train this pre-trained vision model, train it on ImageNet, and directly use the pre-trained model to work in the environment. So first is training the vision model based. It could be training on one episode or training on some data set from the video game. Or in this case, I think they train on ImageNet. And once you have that, then you can sort of use that model directly to fine tune on the policy. And yeah, good performance again. And different layers encode different invariants. So for example, uh, if you are fine tuning different layers of that network, only the last layer, for example, in this case, it reaches good performance. So the conclusion that they came towards is that in tasks such as habitat, where the decisions are more high level, so there are multiple sequence of low level actions. In such tasks, fine tuning just the last layer is enough. Whereas in these environments where uh, manipulation, where you need low level actions, fine grained actions, in that case, if you fine tune the early layers and not the last layers, you reach good, better performance. Now, LLMs as policy. So using LLMs as the representation learning pipeline directly. So the idea here is that you give the task, the prompt, and in addition, you also give a image, an egocentric view of the from the camera, which goes back and it predicts the action directly. So something like this. So you pass the tokens, the visual tokens, the text tokens through the LLM, and the LLM is the policy itself. So it learns to map these tokens to the actions, which is, I think, which is also a good result. More or less the same work. You pass a prompt to the LLM, and I think in this case they collected some data from maybe from human data or RL controller, and use that data to give as a prompt as well in addition to this. And I think during learning it knows the data which it has seen before and uses that to predict the low level actions directly. And so the idea here is that you can use LLM to directly predict actions. So as a policy, as a representation learning itself, because they are very good at, predicting what comes next. So some conclusions: RL representation learning is still is a very vast topic. We covered only a few. Some topics which are of my interest are what we saw: disentanglement learning, temporal learning, and recently pre-trained representations are becoming popular. You train on a big network and then fine tune on your task. So there are still some open questions. How to train those, what to pre-train on, which data sets to pre-train on, and also then using language as a common representation. So I think the goal or the idea here is that how do we incorporate some common sense? We know how to, as humans, we have some knowledge of the task, but we want to use our knowledge to bias the network. And how we do it will make us close to real world RL, I think. I saw some papers from Berkeley which are doing learning directly in the real robot. But I think next 3 to 4 years probably it will become more widely popular. Take a robot and learn directly, skipping the simulation. So if you're interested in any implementations, these are some of the standard ones. This is like my implementation, which I showed before, and these are augmentations and contrastive learning. And that's it from me. If you need the slides, they are at the QR code. Thank you very much.